All right, Gen Chem, today we are going to talk about equilibrium. And we've talked a little bit about it before, but not a lot. So today I want to deepen our understanding of what's happening in equilibrium. We talked about it being dynamic before, meaning that molecules are still moving and going back and forth along that reaction, making reactants are making products, products are being turned back into reactants. We're going to look at some of the mathematical ways and the ways that we can look at those concentrations today. So our next line here in our notes says equilibrium. So I'm right here. Then the line beneath it says that not all chemical reactions go to completion. I would like to actually say most reactions do not go to completion. Most reactions actually end up having some kind of an equilibrium. We do not use up all the reactants, and they don't all get used up to make products. By the time some products are made, some of them are actually decomposing or being changed back into reactants. We have this big circular reaction going on where we have products and reactants just going back and forth all over the place. Okay? So this means that if I have a reaction where I am making B, A doesn't all get used up to make only B. B also gets turned around and made back into A. Reactions go back and forth all the time. So here are a couple of different graphs that show us concentration of different reactions. Let's look at the one on the left first. So if I look at this one on the left, I'm starting with all A. I have no B, so my concentration of B at the very beginning is 0. As A gets made, and I'm going to change my color here, as A gets used up to make B, notice my concentration of B actually starts going up because I'm using A to make B. But at that same time, my concentration of B keeps going up because my concentration of A keeps going down because A is being used to make B. But notice about here, my reaction rate starts slowing down and it starts curving. I don't have this straight line. I don't use up all of A because at this point, B is starting to be made back into A. And notice my concentration of B doesn't go straight up either, okay? Because we're starting to get the reverse reaction, or B going to A, to start being made. And eventually, I get to a point where my concentrations don't change at all. Notice how both of these lines flatten out. Those concentrations don't change at all. Once I get to a spot where my concentrations of all the reactants and all the products that are involved in that reaction do not change anymore over time, even though the reaction is still going back and forth. I have individual molecules going back and forth and being changed from products to reactants and reactants to products. The overall change is 0. This is where I have equilibrium. So notice both of these lines tend to flatten out right about here. This is where we have equilibrium. And I think I put in 2 L's. I think it only has 1. So equilibrium is where we have the rate of the forward reaction being equal to the rate of the reverse reaction. So when the rates of both of those reactions are the same, that means our net change, or our overall change, is 0. But it's dynamic, remember? We do have dynamic because individual molecules are still participating in that reaction. Oh boy. So individual molecules are still reacting. Okay? So now notice here on this first graph that we are looking at, notice my concentration of B. And remember, those square brackets are concentration in molarity, moles per liter, is much bigger than my concentration of A at equilibrium. So this would be a reaction where B, my products, are favored. So my products here are favored. That means I have a lot more products than I have reactants. My reactants are a lot lower in concentration. So yeah, most of my reactants get used up, but not all of them. Okay, let's look at this next graph. Notice we have the same sort of thing. As A gets used up, that curve goes lower and lower and lower. Okay? And as that curve goes lower and lower, B, we start off with none, it gets bigger and bigger and bigger. But notice it doesn't have nearly the same steep curve as the other one. And notice eventually we start flattening out. See that curve right here starting to flatten out? And we eventually do reach a flat line. Right about here is where we reach that flat line. So this is where equilibrium occurs. So right where those lines start to flatten out, that's where equilibrium occurs, okay? Notice though, I don't make a lot of products. My product concentration here is not very big. A is actually our concentrations here. So when our concentration of our product is really low, it really tells us that we have, so my concentration of A, which is my product here, is much less than my concentration of B, which is my reactant. Okay? And when my product concentration is much less than my reactant concentration at equilibrium, this is what we call a reactant-favored reaction. Okay? Because I have more reactants than I have products at the end, at the equilibrium state, at the equilibrium. Okay? So we're going to look at how we mathematically set up some of these things and how we write these expressions. Okay? So let's look at this next line. In the graphs above, both reactions have reached chemical equilibrium. And we showed you about where those started. Remember where those lines start to flatten out, that is where chemical equilibrium happens and starts. Which graph represents the reaction that has produced the most products when equilibrium has been achieved? Is it graph I or graph II? Which one has the most product? Take a minute and circle. Did you circle I? Look at our product concentration. It is really high here. Circle the time on the graphs when you think equilibrium was reached. We didn't circle it, we put in a line. So here's our equilibrium for graph I, and here's the time for graph II that equilibrium was reached, okay? Does equilibrium mean that that reaction has stopped? We talked about being dynamic. Individual molecules are still going back and forth, and they are still reacting, but the net change is zero. So the reaction is still happening. reaction is still happening. It is dynamic. It just is happening at the same rate both ways, so that means the overall change is 0. Okay, let's get into making equilibrium expressions. Now, when we write equilibrium expressions, we always like to do this. We will have an equilibrium constant, and this will be some number. And this is a number. And this number doesn't have any units with it, so you don't really have to worry about units. But when we create an equilibrium expression, we always put the concentration of products on top, and we put the concentration of reactants on bottom. Now remember, I'm using these square brackets. If you remember from our molarity unit, these square brackets mean molarity, which is number of moles per liter. Okay? So that also means that when we do equilibrium constants, we can only put in concentrations, things that we can actually put in 2 moles per liter. And the only substances that we can put into in concentrations are substances that are in the gas phase or in the aqueous phase, which means they're dissolved in water. We cannot put in solids. Solids are not put in, and liquids are not put in because we cannot put them in terms of concentration. Okay? So we only put in gas and things that are dissolved in water, the aqueous things, into these. Okay? So let's do a couple of examples of how we create these constants. Okay? So let's give you this example here. We have nitrogen gas plus 3 hydrogen gases going to make 2 ammonium gases. And notice we have a double arrow, which means that this is a reaction that goes to equilibrium. It goes back and forth as that reaction proceeds. So our products are going to go on top. Our reactants are going to go on the bottom. Now remember, we can only put things that are in the gas state or the aqueous state. Since all 3 of these things are in the gas state, they will all show up. Okay? So we have this going on. We also have to pay attention to our exponents. Our coefficients become exponents. So remember, our products are going to go on top. So our concentration of ammonia is going to go on top. That exponent, that coefficient becomes an exponent. Okay? And our concentration of our reactants go on the bottom. And notice we have no coefficient here. So our exponent can really be a 1, or we can just leave the exponent off because an exponent of 1 is just something that we use to multiply, right? All right. And then this next one, let's see, I want a different color. Our next one, we have our concentration of hydrogen, and that's showing up right here. And our coefficient of hydrogen shows up right there as an exponent. So remember, we have our products on top. We have our reactants on the bottom. And our coefficients, x and y, are coefficients from the balanced equation. Okay? So that is how we construct equilibrium constants. We're going to do a couple of examples for you really quick. Okay? A couple more examples. So let's look at this equation. And I'm going to get a new color. We have 2 carbons in the solid state, and we have oxygen in the gas state, and that is going back and forth with an equilibrium reaction to make 2 carbon monoxide molecules in the gas state. Okay? I want you to take a minute and see if you can figure out how you would write this equilibrium expressions. Remember, in equilibrium expressions, we can only add things that are in the gas state or in the aqueous state. Things that are in the solid state, we cannot add, or things that are in the liquid state, we cannot add because they cannot be expressed in terms of molarity. Okay, so take a minute, draw that equilibrium expression out or write it out. Okay, you ready to check? So where are our products? Our products are carbon monoxide. Is it in the gas state? Yes, it is. So we can definitely add that. So we are going to put our concentration of carbon monoxide. And what happens with our coefficients in the balance equation? Yes, they become exponents. Did you put it as an exponent? Okay, on the bottom, we put our reactants. Okay, carbon. Are we going to put carbon down there? Did you put carbon down there? I sure hope you didn't because it's in the solid state. We cannot put things in the solid state in there. So that carbon is going to be ignored. But oxygen is in the gas state. So that is where we're going to leave this equilibrium expression. Okay? Did you have that for your equilibrium expression? If you put carbon in there, don't worry. Just know that you cannot put in solid or liquid things. Just relearn it. Let's do another practice. Okay? So let's do this one. I've got hydrogen gas plus iodine gas, and I should put the gases here, going back and forth to make hydrogen iodide gas, and I'm going to need 2 of these to balance this out. Take a minute and write your equilibrium expression. Remember, products go on top, exponents become, or coefficients become exponents, and reactants go on bottom, and once again, coefficients become exponents. Okay, take a minute. You ready to check? Okay, this is what I would do for an equilibrium expression of this. Okay, products. We have hydrogen iodide, and it is in the gas state, so we can definitely put that there. Our coefficient of 2 is going to become an exponent. And then that's all our products. So let's look at our reactants. I've got hydrogen, and it's a gas, so I'm going to definitely put that there. So I have hydrogen. It doesn't have a coefficient, so I'm just going to have an exponent of 1 because the coefficient of 1 is implied. And if an exponent of 1 is also implied. I have iodine as well in the gas state, same coefficient of 1, so an exponent of 1, which is also implied. So that is what I would have for my equilibrium constant for this. Okay? All right, one more. Let's look at this one. Let's do magnesium hydroxide in this solid state. Actually, no, I don't want it in the solid state. Let's erase that. Let's put that in the aqueous state. Okay, aqueous dissolved in water, plus 2 hydrochloric acids in the aqueous state, going back and forth to make magnesium chloride solid plus water in the liquid state. Actually, I'm going to change that solid as well to the aqueous state, because that actually will dissolve. That is soluble. Okay, so we've got magnesium hydroxide in the aqueous state, 2 hydrochloric acids in the aqueous state, 1 magnesium chloride in the aqueous state, and water. Okay, take a minute and write your equilibrium expression. Remember, products on top, reactants on the bottom, coefficients become exponents. Okay, you ready to check? Let's look at our products. So our products, we have magnesium chloride in the aqueous state. So it's aqueous. We can actually use it. We can use gases and aqueous. So we would put our magnesium chloride concentration on the top. Okay, what about water? It's in the liquid state. Yeah, so we're not going to show that because it is not something that we can express in the moles per liter calculation. No liquids, no solids, so it's not going to be shown. Okay, let's look at our reactants. Our magnesium hydroxide is in the aqueous state, so we can use that. So we'll have our magnesium hydroxide concentration. There is no coefficient there, so we aren't going to put an exponent there. Then we have hydrochloric acid. That is also in the aqueous state, so that will show up. So our concentration of hydrochloric acid will show up. And we have our coefficient of 2, which is going to become an exponent of 2. Okay, so we would have an exponent of 2. How'd you do on that? Okay, so let's look at this example once again here. We've got another generic equation. We have 2A, 5B, 3C, 4D. We're going to assume that all of these are in the gaseous state. So remember, our equilibrium is always products divided by reactants, and coefficients become exponents. So our equilibrium expression here, our KEQ, would have C, concentration raised to the third, D, concentration raised to the fourth, and then our reactants on the bottom. We would have A, that concentration squared because of that coefficient of 2, and we would have B right here raised to the coefficient of 5 because of that, or raised to the exponent of 5 because of the coefficient of 5. Okay? Another thing that I would like to reiterate that hopefully you saw in those graphs, if K, or the KEQ, is really large, then products are favored. And by large, I mean much greater than 1. So, once again, just a little bit of a reminder. Solids and liquids are not included in that expression or the calculation. Only aqueous and gases. So, let's look at the math here, or our KEQ values. If KEQ, and K is what I mean by KEQ, if KEQ is a large number, meaning much greater than 1, okay? If KEQ is much greater than 1, that means, remember, our products are over our reactants. So if this number is greater than 1, that means I have a lot more products than I have reactants. So that means that products are favored. Okay, I will make a lot more products than I have reactants. But if KEQ is a very small number And these are all positive numbers, meaning much less than 1. So this would be something times 10 to the negative whatever. So this would be a small number. If you wrote it out in scientific notation, it would be like 0.000325, something like that, much less than 1. If this is a very small number, that means that I have a lot more reactants than I have products. So if I have more reactants than I have products, that means this is reactant favored. Okay, so this is how we write equilibrium expression and what those big or small numbers of the equilibrium expression mean. They tell us relative to each other how much product versus how much reactant we can expect to have in this reaction. Okay, so next time we are going to use some of these principles to help us understand Le Chatelier. We'll see you next time. Bye.